the research that my co-author and I have been doing on modeling dust-laden hypersonic flows here at NASA Ames Research Center. The main motivation for this work stems on the need to accurately characterize spacecraft environments when dust particles are present. This is particularly important for the Mars atmosphere where there are frequent dust storms. The other aspect that's being targeted in this work is to get comparative predictions while using physical models of different fidelity. We see this work as being part of a larger multi-physics effort which can fundamentally improve our prediction capabilities. A new particle solver titled Dust has been built for the purpose of this work. Dust works in conjunction with the US3D flow solver to model a variety of particle flow and particle-particle interactions on unstructured meshes. Some of the assumptions and the governing equations underpinning dust have been listed here. I've also tried to highlight the key features that go into ensuring numerical efficiency and allows dust to be used on large-scale practically sized problems. The next step is a series of verification and validation test cases. We've run dust through a variety of test cases that deal with different physical scenarios, and some of them are presented here. The main focus of this work is on determining the particle-induced heat flux experienced by the Mars 2020 spacecraft if its planetary descent were to occur during a dust storm. Some of the simulation details are listed out here, but what's important to note is that the mass loading values that we've considered are still low enough that the two-way coupling between the gas and the particle phases can be ignored. However, the mass loading values are still high enough that particle-particle collisions play an important role. And this is highlighted in the set of two figures present here. So on the left figure corresponds to the lower mass loading case, and the right figure corresponds to the higher mass loading case. And we are trying to predict the total surface heat flux with and without particle collisions. And what ends up happening is for the higher mass loading, there is a distinct difference between the two predicted values. What ends up, so particles undergo inelastic collisions with the wall and then they get trapped in the boundary layer. These particles, the trapped particles, then collide with fresh incoming particles from the inflow phases and they shield the spacecraft surface. Consequently, your total heat flux decreases. This example basically highlights the need to account for all relevant physics while performing these kinds of simulations if we are to design efficient and safe thermal protection systems. Thank you for your time, and I'd be happy to take any